Hello, my name is Taina Matos. I am a PhD candidate at Norfolk State University, and today I'm going to guide you through the usage of FTIR spectroscopy, or better known as Fourier transform infrared spectroscopy. And the reason why we tend to use this is to identify functional groups by their different vibrational modes. So disc-to-disc transparent discs are salt plates used for FTIR, and they're made of sodium chloride. They're very fragile. So the first thing that we're going to do is to sandwich them together and place them on the salt plate holder. And carefully we're going to put the top of it, applying a little bit of pressure without cracking the actual plates. So this is how they look. So in order to place our sample in the FTIR or the instrument cavity, we are going to open it. And we're going to slide our sample holder, making sure that the laser is going through the sample. And you can do that easily by either putting a piece of paper or by placing your hand and seeing the laser beam. Then we close it. Make sure it's securely closed, and we start running our sample. A note, this FTIR, when you're using a purge system, keep in mind that when you open the cavity box, you are letting atmospheric carbon dioxide and water vapor in. So once you close it, you're going to have to let it purge for about 15 minutes or so you will no longer have carbon dioxide and water vapor signals. In order to bring up the software that we use for FTIR, we're going to click on the Opus icon, and we're going to enter the password. And the first window that pops out is About Opus, so we click OK. And the first thing in the screen is you're going to have a variety of different buttons on the top of your page. And the first thing that we want to do is we want to go to Measure. And from Measure, we go to Advanced Measurement. Once the measurement window opens, we're going to go into Basic. We're going to make sure that the experiment is MIR.AXPM. We're going to enter the operator's name, the sample name, in this case, octadecyl phosphonic acid. And after that, we're going to click on Advance. So we already went through the experiment, which is already loaded. We went to the file name, which is the file name that you want your sample to be called. So I will put ODPA, the path that you would like to select, and then we move on to the resolution box, which we want to have a 4 centimeters inverse. The sample scan time is normally run at 16 scans. And the background scan time should be the same or higher than the sample scan time. Then we go to the Save Data box, and it's pretty much the range of the spectrum that you want to scan. So we want to scan from 4,000 to 500 centimeters inverse. Then we move on to the result spectrum, and we want to make sure it's on transmitted. Then we move on to the data blocks to be saved box, in which we want transmitting, single channel, and background to be checked. And after that, we move back to the Basics tab. In the Basics tab, the first thing that we're going to do before we load our sample is to run a background scan of the salt plates that we're going to use. So now we already finished running our background, and we're going to remove the salt plates out of the sample holder. And we are going to put our sample in between the salt plates. And we're going to use a very little amount of sample, just a little drop. And we're going to sandwich the sample in between, carefully placing it again in the sample holder. And now we're ready to run our sample. After the background signal is completed, now we're gonna move on to run our actual sample, and we do that by clicking on Sample Single Channel. After our data is collected, we pretty much obtain a signal or a spectrum in the front page as soon as the experiment is completed. On the y-axis, we have the transmitting, and on the x-axis, we have the range of the spectrum or the wave number in centimeters inverse. These peaks are characteristics of different vibrational modes on molecules, or vibrational modes of the bonds. And specifically in this area around here is between 2900 and 2800, and pretty much this is characteristic of the CH2 stretching of symmetric and asymmetric vibrational modes of carbon bonded to hydrogen.